Okay, good morning, guys. Assalamu alaikum. Welcome back to Inspire Teens, grade 12's physics/chemistry, where in today's lesson, we'll be starting with acids and bases. Okay. I cannot tell, so please, if my screen is not clear, okay, if it's not legible, if you're unable to read, please tell me. Then I can try switching Wi-Fi's or whatever it is to sort that issue out. And yeah, currently the YouTube link is not live for some reason. I'm not sure why it's not letting me. It has done this 1 or 2 times before. For some reason it's not letting me view, so I can't see like what the quality of the screen is. So please let me know, as well as if the audio is clear. If it's cutting, please don't hesitate to tell me and I'll try and fix it. Okay, just make sure that you can hear me clearly, you can see me, and you can see my screen, and all of that is working smoothly. The screen might be slightly blur, but as long as it's legible, then it's fine. Okay, so yes, acids and bases. Okay, and we're going to be starting off with some basics, of course, as we always do. And we're going to discuss the basics. Okay, so the first definition that we're going to discuss, okay, of acid and bases. So when it comes to acids and bases, right, I'm sure by now in grade 12, right, you guys have done a decent amount of acids and bases, okay, in grade 11. And if you remember your grade 11 work, okay, then you should have a somewhat of an idea of what an acid is and what a base is, okay? So let's have a look at these two definitions, all right? The first one is that we're going to go through is the Lowry-Bronsted definition of an acid and the Lowry-Bronsted definition of a base, okay? So Lowry-Bronsted, he says that an acid is a proton donor, okay? And Lowry-Bronsted says that a base is a proton acceptor, okay? So firstly, what we can make sure that we understand is that the proton is an H plus ion. So an H plus ion, we refer to it as a proton, okay? And we're going to use this little chemical equation, okay, to understand that definition and to see how an acid is a proton donor and a base is a proton acceptor, okay? So here we have a little chemical equation, okay? And in this chemical equation, we have NHNO3 plus H2O to give us NO3 minus plus H3O plus. Okay, this is actually an ionization reaction, okay, but that's not so important for now. Okay. Okay, so before I do continue, can I please just get confirmation from someone that my screen is clear and that you can hear me clearly? Actually, I think my screen might be frozen. Let me try to reshare. Okay, sorry, just resharing my screen. I think that's a bit better. Okay, perfect. That's good. That's good. I'm glad to hear. 1 second. Sorry, I'm not home currently, so that's probably why there are technical difficulties. Home is really where the Wi-Fi is, eh? The Wi-Fi that you used to. Okay, so yes, we have this little chemical equation, okay? And it's actually an ionization reaction, okay? Where one of these compounds on the left, okay, donates a hydrogen atom, and one of them receives a hydrogen atom. So the easiest way to tell which one donates and which one receives is by looking at what it becomes on the right-hand side of the equation. So, example, HNO3 becomes NO3 minus on the right, and H2O becomes H3O plus. Okay, so that's what I mean, what it becomes. So what, how, or the change that was made to it, we can tell from observing the difference between what it is as a reactant and what it is as a product. So if we have to look at the difference, okay, between HNO3 and NO3 minus, what we can observe is that HNO3, it lost a hydrogen atom, okay? So it actually, so between HNO3 and NO3 minus, right, it actually loses a hydrogen atom. So what actually happens is this HNO3, okay, it donates this let's do that. It donates the hydrogen atom. My hands are literally freezing. I'm struggling to write. Okay, what it does is it donates this hydrogen atom to H2O. Okay, its hydrogen atom, it donates it to H2O. That's why on the right-hand side, it becomes NO3 minus. Okay, then we can observe H2O. Okay, H2O becomes H3O plus on the right-hand side. And we can see that this H2O is receiving this hydrogen. Okay, and that is further evident when we can see that the H2O becomes H3O, meaning it has now an extra hydrogen. So HNO3, initially it's HNO3. It donates that hydrogen, becomes NO3 minus, okay? And we can see that it donates, it loses that hydrogen. The hydrogen goes to H2O. Initially, it has 2 hydrogen, but at the end, it ends up with 3 hydrogen. So we can see that one is clearly donating and one is receiving. Now, the one that donates, it is known as the acid. The one that donates is known as the acid. Okay, and the one that receives, this little guy here, this guy is known as the base. Okay, this guy, this compound is donating HNO3. We saw what it became on the right hand side. It lost a hydrogen, which clearly means that it had to donate that hydrogen. Okay, and this one, H2O, this is the compound that is receiving that hydrogen. Okay, so this is acting as a base essentially. So here we have an acid, here we have a base. Okay, HNO3 is the one donating, H2O is the one receiving. So because HNO3 donates, we refer to it as an acid. Because H2O is going to receive, we refer to it as a base. And that is Lowry-Bronsted definition of an acid and a base explained in terms of that chemical equation, right? Lowry-Bronsted says that an acid is a proton donor, and we saw it in that equation, right? HNO3, which was the acid, donated the hydrogen atom. Okay, and then we can see it's an H plus ion. Okay, and a base is a proton acceptor. We can see that water is acting as a base here because it's accepting the hydrogen. Okay, so 2 things to note. When you donate a proton, right, a proton is an H plus atom. This H plus atom, this is a proton. It is a positively charged ion. Okay, so when the water accepts a positively charged hydrogen. So I don't know if you guys remember from like basic chemistry, right? A compound like this, CO2, has an overall neutral charge. Okay, so it's an overall charge of 0. Okay, we can compare it to a different kind of compound like SO4. Now SO4 has a 2 minus charge. I don't know if you remember polyatomic ions. Well, you should. Okay, polyatomic ions are very important actually. Okay, SO4 2 minus. This is a chemical compound, okay, that has a negative, there is an ion. Okay, we refer to this as a polyatomic, many atoms, an ion, a polyatomic ion. It has a charge, okay, but a compound like CO2 doesn't have any charge written to it, which means it has an overall neutral charge. Okay, there's no excess positive or negative charges. Okay, so that's what H2O is. Right, H2O has no charge. Initially, it's neutral, has an overall neutral charge. Okay, but as soon as it's given this positive hydrogen ion, it becomes H3O, of course, because it has the extra hydrogen. Plus, now it's actually technically +1. Okay, because now it receives that extra charge, that extra in the form of hydrogen, and that's why it becomes H3O plus. Okay, so that's one thing to observe. The second thing to observe, HNO3 is also a overall neutral compound because it doesn't have a charge like 2 minus or anything. It's just 0 because it's, yeah, we should assume it's 0 because there's nothing written there. And as soon as it gets rid of a single positive charge, it becomes -1. You can see it became NO3 -1. Okay, it got rid of one singular positive charge, which is that H plus ion, and because of that, it became one negative. Okay, because it's losing a positive charge. Okay, so I hope that makes sense, and I hope that's clear. Two things. This becomes negative. HNO3 becomes NO3 minus after it donates the H plus atom, and H2O becomes H3O plus after receiving that H plus atom. Okay, so now so we discussed Lowry-Bronsted theory in terms of this chemical equation where an acid is a proton donor and a base is a proton acceptor. Now we're going to talk about something called acid-base conjugate pairs. It's really simple and it's not as fancy as it sounds. Acid-base conjugate pairs. So the acid-base conjugate pairs, how do we identify which are these pairs? So it's really simple, okay? Why is it simple? Because firstly, we have an acid, okay, on the left, right? And we have to identify its acid-base conjugate pair on the right. And all you have to do is you have to see what is, okay, we have HNO3 on the left. What does it become on the right-hand side? NO3 minus. This is its acid-base conjugate pair. This is its acid-base conjugate pair. Whatever it becomes on the right-hand side is its pair. And because it's acid-base, one is an acid and the other one is a base. Okay, so if HNO3 is an acid, its conjugate base pair acts as a base. Okay, because an acid has a conjugate base pair and a base has a conjugate acid pair. You have to have one of each, okay, in the pair. So in this case, for H2O, H2O becomes H3O plus. So H2O and H3O plus form an acid base conjugate pair. Okay, where of course we have to have one acid and one base. H2O is already acting as a base, so its conjugate pair would be an acid. We call it its conjugate acid pair. Okay, and H2O and H3O plus are conjugate acid-base pairs. So there's two pairs here. The first pair is H3O, no, let's do this in red, HNO3 and NO3 minus, that's an acid-base conjugate pair. And the second pair is H2O and H3O plus, that's an acid-base conjugate pair. Okay, so that's how we determine. So we discussed two things in this little formula. The first thing was Lowry-Bronstet's definition of an acid and a base. An acid is a proton donor and a base is a proton acceptor. So this is an acid-base reaction. Okay, you get different types of reactions if you remember from grade 11, right? Where you learn about the different types of reaction, whether it's redox, whether it's acid-base. Okay, we also have like limiting reagent, those different styles of types of reactions. Okay, and then we have a specific acid-base reaction. Okay, and this is an example of it. When we have a hydrogen being donated and a hydrogen being received, that would be an acid-base pair. Man, I'm really bummed out that this YouTube is not uploading. I have no idea. It's just not, for some reason, not starting the live. It's not allowing me to start the live. Let me try. Sorry, just give me 1 second. Okay, let's start now, I guess. Nothing. Yeah. Mhm. It's okay. I'll upload to YouTube later. It is what it is now. Okay, so yes, yeah, we discussed the Lorentz-Bronsted definition in terms of the chemical formula as well as acid-base conjugate pairs. Please, if you have any questions, let me know. But I think for the most part, that should be fine, right? That should be easy to understand. And acid-base conjugate pairs generally really easy to identify. Okay, and they're still going to ask it in some questions in grade 12. So you need to know it well, and get free marks if it does come up, right? Because acids and bases, the final question can be a bit confusing. Okay, so of course you want to make sure that you can secure your easier marks, okay, for this section, like certainly. Okay. Now, before we continue, before we continue to discussing strong acids and weak acids, we're just gonna have a look at our pH scale. Okay, so a pH scale, okay, or pH is a measurement of how acidic, okay, or how basic something is. So how much of an acid is something, or how much of a base is something. So how acidic it is, or how basic it is. Okay, and here we can see the scale from 0 to 7. We would describe something as acidic. But from 7 to 14, we would describe something as basic. Okay. The closer to 7 we are, okay, and at 7, by the way, so 0 to 7, acidic, 7 to 14 is basic, but actually closer to 7, we would refer to as neutral. Okay, it's more neutral, especially on the dot 7. 7 would be perfectly neutral. Okay, so yeah, right? And then, so if 7 is neutral, the further away from 7 we go on either side, so on the left-hand side, the further away from 7 we go, the more acidic it is. That would make sense because it would be less neutral, okay? So basically, lower numbers are strong acids. So the closer it is to 0, the stronger acid it is, okay? And then the more away from neutral we are towards the right, the more basic it is. So the closer we are to 14, the more basic, the more alkaline. Okay. Remember, acidic and basic are properties. Okay. So yes, this is just the pH scale, which we can use, which we just need to understand these numbers. Okay. Which numbers, which values on the pH scale represent acidic. Okay. Are we back? Um, Let me 1 second. Don't tell me if you can hear me. Okay. Can you guys hear me again? Okay, no, you guys can chat. Okay. You should be able to type now. Please tell me if you can hear me again. I think it's just, okay, no Wi-Fi issue. Let me reshare my screen and then we can continue. Okay, perfect. So, but the technical issues end and don't go on throughout all the lessons. Okay, and now can you see the screen? Is my screen sharing? you know. I hope it didn't cut. Okay, it should be, seems to be fine. Let's just continue, and then if there's any issues, then you just let me know. Okay, so yes, pH scale, right? Very important for us to understand. But pH itself, we will discuss in detail later on, where we will do pH calculations for the first time, actually, because pH calculations are what's new to the acids and bases syllabus in matric. But now let's continue to strong acids and weak acids. Okay, so let's first look at a strong acid. Okay, a strong acid, it says, as little definition says, it ionizes almost completely. Okay, you can ignore the almost, you can just understand it as completely. I'll take it out. Okay, it ionizes completely in an aqueous solution. Now, the key thing that you'll see for the definition of strong acid, weak acid, and strong base, weak base, is this word ionizes, and obviously completely. So acids ionize. Okay, acids ionize, and you'll see that ionization simply means that when we put it in water, okay, it's a ionization reaction is a reaction with water. Okay, so acids ionize, and you'll see that when we discuss bases, okay, bases dissociate. Okay, so just remember that key difference between the two. Acids ionize and bases dissociate. Okay, so a strong acid ionizes completely in an aqueous solution, but a weak acid ionizes partially in an aqueous solution. Then we look at the second point. A strong acid produces a high concentration of hydronium ions. We'll re-explain this one in a bit when we discuss the other definition of acids and bases. While a weak acid produces a low concentration of H3O plus ions. And then we have that a strong acid has a high Ka value and a weak acid has a low Ka value. So what is a Ka value? So the Ka value, Ka itself is simply an acidic constant. Okay, Ka is just something that represents an acidic constant. It tells us how acidic something is. Okay, it's an acidic constant that tells us how acidic something is. How acidic it is. Okay, a certain substance is. And a high Ka value, okay, in order for the Ka value to be referred to as high, the Ka value should be greater than 1. Okay, so in order for it to be considered a high Ka value, it will be greater than 1. And then we have a low Ka value. A low Ka value would be less than 1. Okay, remember that Ka is simply an acidity constant. That tells us how acidic something is. Okay, so now let's have a look at our first reaction for a strong base. So what these are, 1, 2, 3, these are examples of strong bases, okay, and their ionization reactions, their ionization reactions. So these are all ionization reactions. Okay, because remember that acids ionize. Okay, so let's have a look at this first reaction, and where we're going to discuss all the concepts, and then we'll just brush through the rest of the reactions. So right here we have HCl, okay, mixing with water to form Cl minus and H3O plus. Now, whenever this HCl, okay, reacts with water, we call that that is our ionization reaction. Okay, so acids always will ionize. So when they react with water, they will separate into Cl minus. Okay, the H plus essentially gets donated and it will form H3O plus. So what happens here is we also have it labeled, right? We can see that our conjugate acid-base pairs are labeled. We have HCl, okay, pay careful attention to this. We have HCl donating its hydrogen to H2O. HCl donating its hydrogen to H2O. How do we know that? We can see that on the right-hand side, HCl became Cl minus. So it certainly donated that H plus atom. So firstly, it lost its H, so it became Cl, and then it became -1 because it donated a positive ion. So it's because it donated one positive ion, it would become one negative. So the HCl became Cl minus, and then this H2O received the hydrogen ion and became one positive. It became H3O plus. Okay, and that is what an acid ionization reaction looks like, and that's what happens when an acid is ionized. Okay, it donates a hydrogen. Okay, and the other compound, whatever it is, in this case for the ionization, will always be water. Okay, it would form H3O plus. So as you can see, we have acid 1, okay, and base 1. So these are the acid-base pairs, right? HCl and HCl and Cl. Then we have the base, the second base, and the second acid, okay, forming the second acid-base conjugate pair. Okay, so as you can see, this is how an acid ionizes, and this specifically is a strong acid. This is an example of a strong acid, and so too are all of these. Number 1, 2, and 3 are examples, main common examples of the main strong acids that we work with in grade 12, acids and bases. Okay, so yes, once again, this is the ionization reaction of our strong acids. So for all of them, you will see the acid donating hydrogen to H2O. H2O becomes H3O plus. So as you can see, let's just go through this definition, the Arrhenius's definition. Okay, let's see what this guy, this dude, says about acids and bases. So this guy says that an acid, okay, is a substance that produces hydrogen ions or hydronium ions when it dissolves or ionizes in water. So that definition is clear here. An acid is a substance that produces hydronium ions when ionized in water, when dissolved in water. Okay, so that's evident in this equation, and it's evident in all three equations. We can see that this acid being ionized in water to form what? Hydronium ions. In all of them, we have hydronium ions forming, and that is a key distinguishing factor, okay, of an acid. Okay, you'll see that when it comes to the base does not form hydronium ions. Okay, only acids will, and these are all examples of strong acids. Okay, number 1. So let's go through all of these reactions. Let's look at number 2. We have HNO3 plus H2O. Okay, that's going to give us NO3 minus. Okay, why? Because we know that this is acting as an acid, and it's going to donate that hydrogen to this little guy, H2O. So it becomes NO3 minus, and what does H2O form? Surprise, surprise, it forms H3O plus, always, right? We should know that because we know that it's an acid, and this is its ionization reaction. It's going to form hydronium ions. Okay, now let's look at the next one. So this one is important. So then it's important and it's slightly different. Okay. Why is it slightly different, you ask? That is because we have here we have a single hydrogen. Here we have a single hydrogen. And here we have two hydrogens. So the first two, we have one hydrogen. But in the second two, in the last one, we have two hydrogens, H2SO4. And this is known as a diprotic acid. Okay, we'll go through it again when we discuss pH calculations. But this is a diprotic acid. Okay, why? Simply because it has two protons. It has two hydrogen atoms, H2SO4. It's also known as sulfuric acid. Now, when we ionize H2SO4, let's look at this first step here. When we ionize, and we're going to discuss why do we have two steps for this, right? When we ionize hydrogen sulfate, sorry, not hydrogen sulfate, sulfuric acid. It is hydrogen sulfate. No, that's the next one. Sulfuric acid, H2SO4. When we ionize it in water, firstly, it donates one hydrogen. At first, it donates one hydrogen, and therefore it becomes HSO4 minus. So that's fine, right? I hope that should be clear. We have H2SO4. It's an acid, right? It's going to donate one of its hydrogens to H2O. H2O is going to form H3O plus. Perfect. Confirms according to Arrhenius's definition that an acid is a substance when it's ionized, it forms hydronium ions, and clearly that's formed hydronium ions. It's definitely an acid, right? So this acid, H2O, donates one of its hydrogens, forms HSO4, and the water becomes H3O plus. Perfect. Now that's an ionization reaction, right? However, if you look at this conjugate base, I'll tell you why it's a conjugate base, because this is an acid. Whatever it becomes is a conjugate base. Okay. If we look at this conjugate base still has a hydrogen. Okay. So HSO4 minus, HSO4 minus, it still has a hydrogen that it can donate. Okay, so this HSO4 minus can actually act as an acid one more time. So that's why we put this HSO4 through another ionization reaction. So this HSO4 is ionized one more time. So we have HSO4 being ionized in water. Okay, don't worry about the 2 for now. That's just simple balancing. Being ionized in water to form, so HSO4, it's already HSO4 minus. It's going to lose this single hydrogen that it's left with, okay, and it's going to become one more less charged. It's going to become one more negatively charged. So instead of 1 minus, it now becomes 2 minus. It becomes SO4 2 minus, okay, and forms H3O plus. Okay, so H2SO4, we ionize it the first time, it becomes HSO4 minus. HSO4 minus can still be ionized one more time. We ionize HSO4 to form SO4 2 minus, okay, and again, we always form, because it's an acid, we always form H3O plus. So these two display the two levels of ionization for this reaction. We have the first ionization and the second ionization. So diprotic, what you need to remember, diprotic acids can be ionized twice. We can show two ionization reactions for them because they have two hydrogens to donate. That should make sense. They have two hydrogens to donate. They can have a first ionization and a second ionization. Okay, HSO4 is ionized the first time to form HSO4 minus. HSO4 minus it still has one more hydrogen to donate. So it undergoes another ionization reaction to form SO4 2 minus and hydrogens. And of course, SO4 2 minus has no more hydrogen. So it stops at the second ionization. Now, of course, this reaction can actually be represented in one reaction. Okay, where we have H. So okay, so this two here and this 2 here is simply balancing, right? You should actually try and memorize it. It would make life easier that you need to add 2 in front of the hydrogens and H0 to balance it. So we have H2SO4 plus H2O to give us SO4 2 minus plus H3O. Actually, then these are incorrect. Sorry. I'll get rid of them immediately. They should not be here. It's balanced without the 2's. Sorry. Okay. So this here, H2SO4, reacting, ionizing with water, H2O plus or H2O, to form SO4 2 minus plus H3O plus. Now, this is basically the double ionization represented in one chemical equation. Okay, the double ionization represented in one chemical equation. And what we need to do, there's one step that's different. We need to balance it, and that's where the 2's come in. You have to put a 2 there. You have to put a 2 there, and you have to put a 2 there to balance it, and that's it. You just have to balance it. So you can represent, and this double ionization reaction of H2SO4 can be represented in a single chemical equation, okay, provided that you balance it. So just keep that in mind. Okay, this important concept that's written screaming at us here. Strong acids produce weak conjugate bases which don't react with water. We'll come back to that, right? But for now, just keep it in mind. Strong acids produce weak conjugate bases. So what that essentially is telling us is that here we have a strong acid, okay? HNO3, nitric acid, is a strong acid. Its conjugate base is NO3 minus. Its conjugate base is NO3 minus. Okay, so this is a strong acid. Okay, and we certainly know that this is a base because it's acting as a base, right? Because this acid becomes that on the right-hand side, and we know that acid-base conjugate pairs, if one's an acid, the other has to be a base. So this NO3 minus is certainly a base. Now, what this is telling us that if it's a strong acid that you're working with, it will always produce a weak base. So this is a weak base. Okay, so that's essentially what it's telling us. The strong acid produces a weak conjugate base. Let's move on to weak acids. Okay, all right. So weak acids ionize partially in an aqueous solution. That's the definition of a weak acid. It produces low concentration of hydronium ions. So both acids would produce a certain concentration of hydronium ions, right? Because that's a defining factor of an acid. An acid, according to Arrhenius' theory, right, produces hydronium ions when dissolved in water. It's just that when it's a strong acid, it produces a high concentration of hydronium ions, and when it's a weak acid, it produces a low concentration of hydronium ions, okay? Has a low Ka value as well. Let's look at the three different weak acids that we're going to discuss. The first is, okay, and by the way, for all of these, I've noted some common names, which you should know. For example, hydrochloric acid, nitric acid, sulfuric acid, hydrogen sulfate, which either way, you should know, right? So let's look at this. We have CH3COOH, which is ethanoic acid or acetic acid, or it's common, it's vinegar essentially. Or we have COOH2, which can be written as H2C2O4, or it's also known as oxalic acid, or H2CO3, which is also known as carbonic acid. Okay, so you must note the common names. More commonly tested in grade 11, but it does not mean that they can put in carbonic acid reacts with this and then expect you to understand and know what carbonic acid is and what its chemical formula is, right? So you should know it either way. So let's have a look at this reaction. So firstly, before we do anything, we can see that, okay, this little guy, it's busy in a reaction, but at the end, hydronium ions. So for sure, it has to be an acid. Okay, immediately just after up, we know that for sure that it's an acid because it's forming, according to Arrhenius' theory, according to Arrhenius' theory, an acid forms hydrogen ions when dissolved in water. We can see the hydrogen ions forming there. So this is definitely an acid. Okay, so what happens is with this one specifically, don't confuse it. How do these two react? They actually react with CH3, CH3, COO minus, and H plus. Okay, this is the anion and this is the cation that join to create CH3COOH. Okay, so that H plus hydrogen is that extra hydrogen. So because it's an acid, albeit it's a weak acid, right, it still donates the proton to hydrogen. It still donates the proton to water, H2O. H2O becomes H3O plus. This becomes CH3COO minus. Okay. Yes, what I wanted to say. No, that should be fine. Then we have COOH2, okay, and it donates this H here, okay, and it forms, because there's two hydrogens here, actually, this is also like a diprotic acid, and it would have, it is also like a diprotic acid, and it would have a double ionization as well. Okay, so in this case, we've just represented it in one equation, and we've balanced our hydrogens and waters. We would balance our hydronium and our water. Okay, so here we have the acid donating two of its hydrogens, actually forms hydronium ions, and this becoming a negatively charged ion. Okay, and so too is the same for that. It becomes a negatively charged ion because it loses its positive hydrogen atom, right? Then we have H2CO3 plus 2H2O, giving us CO3 2 minus to form hydronium ions. Again, diprotic acid, double ionization shown in one step. Just we make sure to balance the water and the hydronium ions. Okay, so these are the weak acids, right? So as you can see, between the strong acids and the weak acids, they both produce hydronium. Just understand that these would be high concentrations of hydronium, and these would be low concentrations of hydronium, but both are hydronium. Okay, so those are our ionization reactions for strong acids and weak acids. Is it only the reactions with weak acids that are reversible? Yes, I think so. I'm not 100% sure. I'm going to confirm that for you. But irrespective, it's not like too important for this section specifically. Like it won't matter at all in answering questions, but I will confirm that for you. Okay. So yes, ionization reactions. For strong acids and weak acids, it's important to understand these reactions properly and be able to draw these reactions, because oftentimes certain questions do actually require you to give the answer as the equation. So they'll ask you a question, and the answer for that question is actually you writing out an ionization reaction for one of the acids. Okay, so it's very important for you to understand how these reactions take place, okay, and which ones we need to balance and how do we balance them. Okay, it's like advisable, in my opinion, to just memorize all of these. They're not that difficult, right? Once you get the concept remains the same. But the chances that you're going to get a question that asks you to write the ionization reaction for HCl, for example, are really high, and HCl is here. Okay. So yes, then we can discuss this last final concept that says that weak acids produce strong conjugate base pairs. So this guy, okay, this guy is a weak acid. So its conjugate base would be a strong base. Always opposite. Okay, weak acids produce strong conjugate base pairs. Okay, and strong acids produce weak conjugate base pairs. Okay, cool. You'll see, we'll note later on in questions as well, we're going to do all the common bases, but not all of them. Like there are a larger pool of bases that could be used actually in an exam question that we're going to discuss when we discuss these. Okay, and that comes from this conjugate base pairs, right? So we know that a weak acid, or an acid in general, right, has a base conjugate pair. An acid has a base conjugate pair. So this guy could be reacted with something else to form a base. Like for example, it could react with a metal such as give me a periodic table. Okay, such as magnesium, okay, or even calcium. We could have CaCO3. And this is not a base that we will discuss specifically, but it could act as a base. Why? Because you need to remember that this CO3 2 minus, it's CO3 2 minus, it's just reacted actually with Ca2 plus. That's why it forms this CaCO3. So this is actually Ca2 plus and CO3 2 minus. This CO2 minus, CO3 minus, in this specific reaction, okay, this weak acid is forming the strong conjugate base. So CO3 minus is a base. So they could use CaCO3 as a base. Why? Because the CO3 minus is actually a conjugate strong base from this reaction. Okay, it'll make more sense when we do a question. But nevertheless, remember those last things, that strong acid produce weak conjugate bases which don't react with water, and weak acid produce strong conjugate bases. Now let's discuss the bases. A strong base is a substance or a base that dissociates completely in water. So bases dissociate, okay? And a weak base dissociates partially in the solution, okay? A strong base produces a high concentration. So those square brackets represent concentration. If you remember from equilibrium, we discussed that. That a strong base produces a high concentration of hydroxide. So this is known as hydroxide. Okay, these are hydroxide ions. Okay, and the other one, the H3O, is known as hydronium. Okay, these are hydronium ions. Okay, so strong bases and weak bases. One dissociates completely, one dissociates partially. Strong bases produce a high concentration of hydroxide ions, while weak bases produce a low concentration of hydroxide ions. A strong bases would have a high Kb value, so you can assume that a Kb value is essentially a basic constant, okay, or an alkaline constant. Okay, that tells you what? That tells you how basic it is. Okay, how basic your base is essentially. Okay, and a high Kb value would be considered a Kb value greater than 1. And a low Kb value would be considered a Kb value less than 1. Okay, so keep that in mind. Similar to our acids, right? It's just now we have Kb instead of Ka. Okay, so let's look at the first reaction. NaOH dissociates. So this is how we actually show a dissociation reaction. So if you remember the ionization reaction, we added water, okay, and the compound ionized in water, okay? But now, in order to show dissociation, we don't add it to water. We could show the water on the arrow to indicate that it is dissolving or dissociating, better phrased, in water, okay? And it dissociates to form Na plus and OH minus. It basically dissociates to form its ions, okay? And we can see that, okay, yes, we do refer to this as a strong base. We need to memorize our strong bases and all of the common ones, okay? We can see that when a base is dissolved in water, or so a base dissociates in an aqueous solution, okay, it forms hydroxide ions. Sorry, yeah, it forms hydroxide ions. And going back to my guy's definition, Arrhenius himself, okay, he defines a base as a substance that produces hydroxide ions when dissolved in water. Okay, so this definition can be seen in this equation here, that when a base dissolves in water, it forms hydroxide ions. Okay, so that's how we can see Arrhenius's definition of a base in a chemical reaction. Okay, so NaOH, KOH, and LiOH, so sodium hydroxide, potassium hydroxide, and lithium hydroxide, all dissociating completely in water, okay, because these are strong bases, okay, and they're clearly forming, right, OH minus, OH minus, OH minus. This is indicative of a base, okay? This is a distinguishing characteristic of a base. A base produces hydroxide ions when in water, when dissociating in water, Okay, and importantly here as well, strong bases produce weak ions. Okay, so this is a strong base. And it produces weak ions. Okay, and let's move on to weak bases. So they dissociate partially in the solution. They produce a low concentration of hydroxide ions, right? So strong base, high concentration of hydroxide, weak base, low concentration of hydroxide. And of course, a weak base has a low Kb value. So here we have the two common low weak bases that we can discuss. And why is it an arrow? Okay, this is an exception, right? So for most basic reactions, right, or if we're showing the dissociation of a base, okay, we show the dissociation without reacting it with water. Okay, we just simply show it like that, and its dissociation can be seen separated into its ions. Okay, however, this is a slight exception to that rule. Okay, when we have the base NH3. Okay, here NH3 is acting as a base. Okay, and NH3 becomes NH4 on the right-hand side. So clearly it received, that's why it's acting as a base. So its conjugate would be an acid. Okay, and in order for NH3 to act as a base, this one has to act as an acid. This H2O, it has to act as an acid. So H2O is acting as an acid. Hey, man. This is acting as an acid. And its conjugate pair is on the other side, which would be acting as a base. Okay, so we can see the conjugate acid-base pairs here as well. NH3 acting as a base, receiving that hydrogen. Okay, and H2O acting as an acid. So whenever we show the dissociation of water, H2O acts as an acid. Sorry, whenever we show the dissociation of a base, H2O acts as an acid. But when we show the ionization of an acid, H2O acts as a base. Okay, that makes sense. Okay, and one thing also to note that on one side of the equation, if one of them is a base, the other one will be an acid. Okay, in this case, if this is an acid, this has to be a base and vice versa. As well as the same concept applies for conjugate acid-base pairs. If this is your base and you have a conjugate pair, it has to be an acid. If this is an acid and you have the conjugate pair, it has to be a base. Okay, always opposite. So just cool, keep that in mind. Then we have NH4OH that would form this. We show this the dissociation of it, forming NH4 plus OH minus. Now, what's important to remember is weak bases produce strong conjugate acids. Okay, so the similar concept that we've been discussing. A weak acid, okay, sorry, a weak base forms a strong conjugate acid. So weak base, not bases, and a strong acid. Okay, so it's always opposite. Strong acids produce weak conjugate base pairs. Weak acids produce strong conjugate base pairs. Strong bases produce weak conjugate acids, and weak bases produce strong conjugate acids. So it's opposite. A lot of opposites going on here, actually, now that you think of it. Okay, so yes, let us end it there. That's our strong acids, weak acids, strong bases, weak bases. Very important. Right, next time we will continue. Okay, we'll try and finish up all the conceptual ideas of acids and bases. Okay, and then eventually, of course, move to calculations which can get pretty tricky, right? Especially when we're talking about neutralization, when we're talking about limiting reagent, we're talking about access, as well as pH. Okay, we're going to try and simplify all of those concepts. Okay, so please make sure to not miss those lessons. And again, those can get confusing. So we can make use of the Q&A sessions at the end to try and clarify all your misconceptions, all your misunderstandings. Okay, but yeah, let's end it there. I'm going to leave it open for the next few minutes. If no one has any questions, I'll end it. quickly because we need to start the next lesson, but I'll wait to see if anyone has any questions and I will attend to your questions. Okay. Okay, here's a good question. Are we going to get to a point where we do calculations with KB or KA value? No, we will not. That's not required for us to know KB or KA value, all right? I will double check syllabus for 2023, but no, that's not that's not required. You're not required to get to that point. We will do KC in equilibrium. KC is also like a constant of the concentrations at equilibrium. Okay, similarly to how this is a constant of the bases and this is a constant of the acids. But you won't be required to use those calculations, to do those calculations. Okay, cool. Doesn't seem like there's any other further questions, and we're running late for the next session. So let's end it there. If you do have any other questions, you can feel free to message me. How do we identify the conjugate pairs with the dissociation of bases? There's no need. There's no need to identify it in the dissociation reactions. Yeah, don't get, you see the thing about, the chemical syllabus is like for high school, not everything, because chemistry can get quite complicated, right? There's certain things that are like not discussed or taught in details, okay? So there's certain things, there's a lot of things that are always like a bit ambiguous, right? And like one of those things is because like there's so many exceptions, like random exceptions, just because of the nature of chemistry. like the NH3 reaction that we show with H2O, the dissociation reaction we show with H2O, but the other reactions of like strong bases, for example, that we don't show H2O, okay, like that exception. So there won't be a need to identify conjugate pairs in the dissociation of bases. Like when you identify conjugate acid-base pairs, it's going to be acid-base reaction where you're going to clearly be able to see an acid and a base and an acid and a base. You're going to have at least two on each side. Okay, so don't worry about that. You will not. The reaction given to identify acid-base conjugate pairs would be two on each side for sure, certainly. Okay, but yeah. Feel free to ask many of those type of questions for chemistry because, like I said, there's a lot of things that are sometimes up in the air, which is actually annoying about the chemistry syllabus. But yeah, it just is what it is. No problem. You're welcome. I think it was you. Yeah, I'll get back to you on the reversible. But like I said, I'm pretty sure it is only those. Like the ones that I have reversible are the ones that are reversible. And I would just learn it for the, as to like to answer the question. Like I would learn which ones are reversible, right? But like I said, it's not going to be a train smash when it comes to this section. Because that's not the concepts that they want to test. They're not going to test whether you know if it's reversible or not. The concepts they want to test is more related to acids and bases and pH and calculations. And obviously in the theory aspect, it's like what is a strong base, weak base, understanding ionization reactions and how to identify an acid, how to identify a base, conjugate acid-base pairs, and those types of things. Okay. But yeah, what I'll do is I'll just confirm that the ones that I have reversible are the only ones that are reversible. But yeah, okay. Let us end it there though. So if you do have any other questions, just message me or save it for next week. Just because I want to start the next lesson. But thank you guys so much for joining. Go have a good week at school. Actually, I'll see you guys later at 11 for chemical equilibrium. So yeah, see you guys later, I guess. Jazakallah khair. Thank you. Assalamu alaikum and goodbye for now.